Alright, here we go with the Chapter 5 Homework 2 review, the second of two assignments for Chapter 5. Still dealing primarily with topics related to stoichiometry. Average this week was 10.03 out of 12, so just above 10, pretty typical for this time in the semester. So what I'll go over here are about 7 or 8 questions that we had where the success rate was about 60% or less. In other words, in all these questions, 60% or less of you got these right, so we just want to make sure we address these and understand any of the problems that we had. If you have additional questions on the homework, please come see me. Keep in mind that the next exam starts in 1 week, so you're going to want to start addressing your questions right away if you have any. Alright, so let's get on to the first one. So a lot of the questions on this homework assignment required us to balance a chemical equation, and this was the only one that was exclusively about that topic that we had some trouble with. It is a little bit of a tricky one, as we'll see, but we just have the following unbalanced reaction with lead, water, oxygen, and then forming lead hydroxide. And we want to know what are the coefficients for lead and water respectively. I think this was a multiple choice question. I don't have all the choices listed here, but unless we're told otherwise, we want to try to balance these with whole number coefficients and then see what the coefficients are that we're asked about. This one doesn't specifically say to look for whole numbers, so that may have been a source of confusion for some of you, but if we don't specify, please do use all whole number coefficients, the smallest whole number coefficients that are possible, because it is possible to balance reactions with fractions as we see, but we don't want to use those when we're trying to select our final answer. So let's see how that works in this case. We have lead, water, and as I talk about in class, what I typically like to do is take whatever I think is the most complex species, which usually is the one that has the most elements in it, and set that to a coefficient of 1. So we're going to do that here, and I like to put this as 1 because it has all the elements, it's the only product. And then from there, what we want to do is look at the reaction side and find out which elements only appear once. So we see that lead only appears once in elemental lead. So if we have 1 lead hydroxide as a product, we need 1 Pb, 1 lead, on the reactant side. And then similarly, hydrogen only appears once as well. So it appears once on the product side, once on the reactant side. So that one we can balance pretty easily as well. We have 2 hydrogens in our product, and so we need 1 water to give us 2 hydrogens on the reactant side. And then the last thing to look at is oxygen. So oxygen appears twice on the reaction side, which is why I want to balance that last. So on the product side here, we have 2 oxygens, 2 OH minuses for a total of 2 oxygens. By adding 1 water, we added 1 oxygen, so we need 1 more. And so if we have an O2, we need just 1 oxygen from O2, we would put a half in front of it. So that is a correct balanced form of this chemical equation, but as I said, when we're answering questions on Blackboard, assume, unless we tell you otherwise, that you want to use whole number coefficients. So since we have a fraction here of 1/2, we need to double every coefficient to get rid of that. And so the final form of our chemical equation is 2 leads, 2 waters, 1 O2 to get rid of that fraction, forming 2 lead hydroxides, PbOH2. Alright, so that's the final balanced form of this equation. This is asking for coefficients of lead and water, so it would be 2 and 2. Alright. It is possible to balance this with coefficients of 1, but that requires you to have a fractional coefficient. And so in the final balanced form of the equation, we want to get rid of fractions, and this is the correct way to do it. Alright, so as I said, we're going to see a lot of questions on this assignment that require us to balance equations. This was the only one that was specifically about that we seem to have a little bit of trouble with. So hopefully that clears things up there. Alright, now surprisingly, the question we did worst on was more of a conceptual type question. It's true and false, which means ideally we should get 50% success rate, but the success rate was more like 37. So clearly we had some trouble with this one, and so we want to talk this through. So this one deals with the concept of limiting reactants, and as we said in class, limiting reactant is the one that determines how much product can form when you mix 2 amounts of, or 2 or more reactants together. So here we have the equation 3A plus B goes to C plus D. We're reacting 1 mole of A with 3 moles of B. And the question is true or false. A is a limiting reactant because you have fewer moles of A than B. Well, let's first see if A is the limiting reactant. Remember that the way we do that is not just based on the number of moles, it's based on what's called the stoichiometric ratio. So the stoichiometric ratio is going to be the number of moles of that substance we have. For A, it's going to be 1 mole. Then we divide that by the coefficient in the balanced chemical equation, which is 3. So stoichiometric ratio for A is 1/3, and then for B, we take the number of moles of B that we have, which is 3. So here we don't even have to calculate the number of moles, they're given to us. And we divide that by the coefficient for B, which is a 1. There's no coefficient, so it's 1. So because the stoichiometric ratio for A is smaller, A is limiting reactant. So that part of the statement is true, A is limiting reactant. However, the reason why it's true is false. A is limiting reactant because you have fewer moles of A than B. Now, just because you have fewer number of moles of A does not mean it will be the limiting reactant. We saw some examples in class where one reactant had fewer moles, but it was still not the limiting reactant because of when you have to divide by the coefficient. So this statement is going to be false, not because the first part of it is false, but because the reason we're giving is false. Okay, so you cannot just use the number of moles to tell you that something is limiting reactant. It has to do with the method I use with these stoichiometric ratios, or alternatively it's determined by which of these reactants will form fewer moles of products. There's a couple ways of looking at it, but it's not just number of moles that dictates limiting reactant. Alright, so that was a conceptual question, and I think many of us just sort of rush through this thinking, well, A is limiting reactant, so this must be true, but the second half of the statement, the reason for that, is the part that makes it false. Alright. Now let's move on to some more numerical questions. So this first one here, we're doing the reaction of N2 and H2 to produce NH3. We want to know how many moles of N2 will produce 36.2 moles of NH3. So this is what we would call a mole-to-mole stoichiometry problem. We're giving you moles of one species and we're asking you to calculate moles of another species. So we have to first write out the balanced chemical equation. N2, H2 going to NH3. We want to use whole numbers, and N2 means we have to have 2 NH3s, and now we have 6 hydrogens, so we need 3 H2s. So this is the correct chemical equation, N2 plus 3 H2 going to 2 NH3, relatively straightforward to balance. And now from here we can go and solve the problem. We're looking for how many moles of N2 will produce 36.2 moles of NH3. So this is what we're looking for, is moles of N2. And we're told that we want to produce 36.2. Now remember, we can start in the stoichiometry problem with an amount of a reactant or amount of a product and calculate any other amount that's associated with this reaction. So we have 36.2 moles of NH3. And this is a pretty straightforward question now because we already have moles of product. So if we want to calculate moles of reactant, we just have to use the coefficients. So we're looking for moles of N2, so we want that in the numerator, and moles of NH3 in the denominator. And we just go, to get this ratio, we just look at the coefficient. So N2 has no coefficient in front of it, so that's 1, and then NH3 is a coefficient of 2. And that's all we have to do, is just one step here because we're just converting between moles. And so we just divide 36.2 divided by 2 and we get 18.1. Now this was a numerical question, so you would just enter in the answer with whatever precision we specified. And I think this is a fairly straightforward problem. It's just that we tend to do a little bit worse on the numerical questions than on multiple choice because we don't get people guessing correctly. So anyway, this one is just a one-step mole-to-mole calculation. So if you have moles, then you can go ahead and use the stoichiometric coefficients right away. When we're doing stoichiometry, our first goal is to get into moles of one of the substances. Here is given to us directly, so that eliminates a step that we often have. Now this next question is very similar, same chemical reaction, N2 and H2 to produce NH3, but now we're looking for how many moles of H2 will produce 75.3 grams of NH3 if sufficient N2 is present. So that tells us that H2 is a limiting reactant. And we want to know, which isn't really important for this question, I should say. So it's another numerical question, and this time it's just a little bit different because we're given grams of product and trying to find moles of one of the reactants. So there's going to be one more step, as we'll see. So it's going to be the same chemical equation. N2 plus 3H2 going to 2 NH3s. And what we're looking for here this time is moles of H2, not moles of N2. So that's what we're trying to find. Sorry, this keeps skipping on me. I don't know why. Okay, so we're looking for moles of H2. And we want to find how many moles of H2 are required to produce 75.3 grams of NH3. Alright, so remember that stoichiometric coefficients have nothing to do with grams, they're all about mole ratios. So whenever we're given an amount that's a mass amount, we need to convert it into moles first. So when in doubt in a stoichiometry problem, convert to moles. That's never a bad thing to do. So we're going to convert to moles of NH3 by using the molar mass. We have to calculate that. The molecular weight for NH3, I'm not going to go through the calculation, is going to be the atomic mass of nitrogen plus 3 times hydrogen, which is 17.03 grams per mole. So we convert to moles by using the molar mass. And we're going to divide by the molar mass so that grams cancel, and we get moles of NH3. Now that we're in moles of NH3, we can calculate moles of H2 using coefficients from the balanced equation. We want moles of H2 on the top, moles of NH3 on the bottom so that it cancels. And the ratios are 3 moles of H2 for every 2 moles of NH3. So the ratio is going to be 3 to 2 in this case. Moles of NH3 cancel out. We have the unit that we want, which is moles of H2, so we stop there and just calculate out. So 75.3, we divide by the molar mass, multiply by 3 over 2, and we get, in this case, 6.63 moles of H2 using the correct number of significant figures. Alright, and this again was a numerical question, so the numbers you had were probably different because there was a lot of different possibilities and I just chose one randomly, but the steps are the same. Grams to moles and then using coefficients to get moles of the other substance. And then finally, one last variation we have on stoichiometry problems, which was another one that, this was another numerical question we had a little bit of trouble with, is what's called a mass to mass. So we have 5.236 grams of C4H10, and we want to know how many grams of CO2 we'll get when we burn that. Now we haven't yet learned how to fully write out a combustion equation. We'll get to that, I think, a little bit later in chapter 6. Or maybe a little bit, even after, I forget when it is. We'll talk about combustion in more detail in a little bit. We don't know the full details, but what we should be able to tell right away is when we burn something, as we talked about in combustion analysis, this is not going to be the full thing, but all of the carbon is going to go into CO2. So even if we don't write out the full balanced chemical equation, what we should recognize is that if we have 1 mole of C4H10, all of the carbon goes into making CO2, so we need to have 4 moles of CO2. So this is not a perfectly balanced equation. If we want to write out the full thing, it would be C4H10 plus O2 going to CO2 and water. So this is a full combustion equation, but not terribly important for this question because we're just asking about C4H10 and CO2. So as long as we know that those are in a 1 to 4 ratio, and this is, let's see, 8 plus 5 is 13, so this would be 13 over 2. So that's another way to balance if you want to write the full equation, or we could get rid of the fractional coefficients and write and this would be the balanced chemical equation without any fractions. So there's a lot of different ways we could do this. All that really matters for this question is that the ratio of C4H10 to CO2 is 1 to 4. 4 CO2s for every C4H10, or alternatively 8 for every 2. However you chose to write this equation, or whether you just wrote out the partial equation like I did here, as long as you know that they're a 1 to 4 ratio, that's going to be the key piece of information we need. So now we want to know if we burn 5.236 grams of this reactant, how many grams of CO2 will we get? So we're looking for the mass of CO2. We have 5.236 grams of C4H10. And like I said, in the stoichiometry problem, we should convert to moles first, so we'll use the molar mass to get moles of that substance. So we need the molar mass, which is 4 times carbon plus 10 hydrogens. So the molar mass for this is around 58.12. Alright, so that gives us moles of C4H10, and then as we said, in a lot of different ways you can figure this out, that there should be 4 moles of CO2 for every 1 mole of C4H10. And then we're looking for grams of CO2, so this is a mass-to-mass question, so we have one last step, which is to convert the moles of the second substance back into grams using its molar mass. We want grams of CO2 for every mole. And the molar mass of CO2 is 44. So moles cancel out, and that gives us into grams of CO2, which is what we're looking for. So this had a few more steps because we had to convert from grams into moles and then moles back into grams at the end. But it's the same types of conversions we've been doing for a while now. And assuming I did my calculator math correctly, got 15.86 grams of CO2. This was one of the numerical questions, and you just enter in the number 15.86. Alright, that looks weird. Let me double check that. And I think that's the right number. Okay, so that's a typical mass-to-mass stoichiometry problem. Here, it may not have been possible at this stage in the course for you to write these full balanced chemical equations, but as long as we recognize a 1:4 ratio here, this was the key part here that we needed to know, that's going to give us the answer, however we choose to do this, okay? Alright, so this next question here was sort of a conceptual problem, although a little bit numerical as well, so kind of a combination of two things. So we have the reaction between AB2 and B2. Now we're not told which is which, but based on that information, we look at the reactants over here. That means the black ones are A, and the orange ones are B. So we have these different colored atoms here. AB2 is 1 black and 2 oranges, and then B2, 2 oranges. So those are the reactants, and that's how they're sort of color-coded in these pictures. And then we see that the only product that we're forming is this guy here, which is AB3. We have some leftover B2. Now, the point of this question is we don't want to use the pictures to try to answer the question. We want to use the numbers that were given. So this gives us one scenario where we're reacting the two species, but we want to actually use the numbers that were told, 5 moles and 3 moles, to figure out how many moles of B2 would be unreacted. So we need a balanced chemical equation first, and really that's all this picture is going to help us do. We have these two pictures here, and it's just telling us that the product is AB3, so when we have AB2 plus B2 going to AB3. So we do need a balanced chemical equation. If we want to use whole numbers for this, we would have to do, I think, 2, that's, I think, the balanced chemical equation, 2 to 1 to 2 ratio. Let's see, 2 A's, 4 plus 2 is 6 B's. So that's how we balance it with whole numbers. Again, you could have started with fractions on B2 and then multiplied by 2. So this is what we get for a balanced chemical equation. So that's really what the pictures allowed us to do. And then from here, we just approach this like a typical stoichiometry problem. So we have 5 moles of AB2, 3 moles of B2. We have amounts of both reactants, so we need to figure out which one is limiting. So we use these stoichiometric ratios for AB2. We take the moles of AB2, which is 5, and we divide it by the coefficient in the balanced equation, which is 2. So that's 5 over 2, or 2.5. We do the same thing for B2. We have 3 moles of B2, and we divide that by its coefficient, which is a 1, and so the stoichiometric ratio for B2 is 3. So that means that AB2 in this situation is the limiting reactant, because it has the smaller stoichiometric ratio. And that tells us then that we're going to have some B2 unreacted. So we know that the answer won't be 0. Now we have to figure out what the answer actually is. And so to do that, we're going to find how many moles of B2 are actually consumed in this reaction. So we're going to use stoichiometry to figure out if we have 5 moles of AB2, which is our limiting reactant, how many moles of B2 will react with that. So we always start with our limiting reactant, 5 moles of AB2. And then we use coefficients to figure out how many moles of B2 will react with that. So we have 1 mole of B2, this coefficient is 1, reacting with 2 moles of AB2, so it's going to be a 1 to 2 mole ratio. So 2.5 moles of B2. And then finally, the moles of B2 that are excess is the amount we started with, which is 3. Sorry, that's not that number, but we have, as we're told in the question, we have 3 moles of B2. We reacted 2.5, and that means we have 0.5 moles in excess, and that should be the answer that we selected. I think this was multiple choice. Okay, so this one required us to use the pictures to help us get a balanced chemical equation, but once we had that, it's just a standard limiting reactant problem where we're determining how many moles of the excess reactant there are. Alright, this next question, which I think is the last one, is one more limiting reactant problem. Now here it's not necessarily labeled as such, or it's not obvious from the question, but we're doing the reaction of calcium with sulfur to form calcium sulfide. We want to know the theoretical yield that can be prepared from 2.75 grams of calcium and 2.50 grams of sulfur. Now we're told right here that we have mass amounts of 2 reactants, calcium and sulfur. So anytime you're given amounts of 2 reactants, you should recognize right away that we have to determine which of those reactants is the limiting reactant. But first we need a balanced chemical equation. So at this stage of the course, we're not familiar with the standard forms of the elements, although it doesn't matter in this case. So what probably most of us did, is we wrote calcium plus sulfur, which is also solid. Not that it really matters, it takes a matter. And the formula for calcium sulfide is going to be calcium 2 plus S2 minus, so reviewing ionic compounds. Let's figure out how we did that. So we have calcium sulfide. Calcium is in group 2A, so the formula is 2 plus cation. Sulfur is here in group 6A, so it's going to form a 2 minus anion. So that's a review from chapter 3. And so that means the formula for calcium sulfide is CaS, so that's going to be our product. And this was the simplest way to just write the chemical equation, calcium plus sulfur going to calcium sulfide. Now something we'll learn later on in the course, and something some of you may have already known or even looked up as part of this problem, is that technically the elemental form of sulfur is S8. And so then we would get still calcium sulfide. And if we balance this one with full numbers, we would get an 8 there and an 8 there. Now this may look like it's way different, but it actually ends up is really the same thing from a numerical standpoint. So however you chose to write this balanced equation, whether you use just monoatomic sulfur or the correct elemental form S8, both of these will give you the same answer in this question, so it doesn't matter how you did it. But these are 2 alternative ways of balancing the equation. Now I'm going to use the one that's technically correct, that has S8 as a reactant, but it's not terribly important that you use this one as opposed to just doing the top one. Either of these will work, but I'll use the one that's technically correct. As we'll learn, I think in chapter 7, S8 is the correct form for sulfur as an element. Okay, so if we have 2 reactants and we have amounts of both of them, we have to figure out which one's the limiting reactant. So the first thing we do is find moles of each. So the moles of calcium, we have 2.75 grams. And we're going to use the atomic mass of calcium to convert grams into moles. So 1 mole of calcium has a mass of 40.08 grams. That's from the periodic table. I won't go to right now, but that's where you get that number. And so the moles of calcium we have are 0.0686. And then the stoichiometric ratio. Remember, the number of moles doesn't tell us directly whether it's limiting reactant or not. We need what's called the stoichiometric ratio. So we take that number and we divide it by the coefficient, which in this case is 8, if I use the bottom chemical equation. And we get 0.00858 is the stoichiometric ratio. And then we do the same thing for sulfur, S8, or just acid, we use the first equation. So we have 2.5 grams of sulfur So if we're using it as S8, we use the molar mass of S8, which is 8 times the atomic mass of sulfur. So that's going to be 256.56. So that converts grams of S8 into moles, which is 0.00974 moles. And I should reiterate again that this is one of those questions with variable numerical input, so the numbers you have are probably different, but it's the same series of steps. And then what we do from there is we find the stoichiometric ratio for S8, which is taking that number and dividing by the coefficient. So if we're using this bottom equation here, that has a coefficient of 1, and so the stoichiometric ratio is just the same number. And we can see that this number here is a little bit smaller, so calcium is our limiting reactant. Okay? Now, as I said before, once you have what the limiting reactant is, once you use the stoichiometric ratio, we're done with it. And all of our calculations will now start with the amount of calcium. So we could either go back and start with mass of calcium, or since we already calculated moles, that's probably the more logical place to start. And so what we're looking for is the theoretical yield in grams of calcium sulfide. So we're looking for the grams of calcium sulfide. And our limiting reactant is calcium. We have 0.0686 moles of calcium. And since we already have the moles of our limiting reactant, we can now find the moles of product using the coefficients. Okay, so we have, from the coefficients, we have 8 moles of calcium sulfide per 8 moles of calcium. And what we're looking for is grams of calcium sulfide. So we now need to multiply by the molar mass of calcium sulfide, which is just the sum of the two atomic masses, 72.15. And so when we multiply this out, we get 4.95 grams of calcium sulfide, and you would just enter in the number 4.95. Alright, so another mass-to-mass stoichiometry problem, but this one also required us to find limiting reactant first before we did the calculation. If we had started the calculation with the amount of sulfur we had, we would have gotten a larger number. So the other way to do this is just to do the calculations twice. It's probably a similar amount of work actually in this case. You would just do the calculations twice, one starting with calcium, one starting with the mass of sulfur, and you would pick the smaller of the two numbers because the limiting reactant is going to limit how much of the product can form. Alright, so that takes us to the end of this one. There were a few other topics in there like percent yield and things that we seem to do pretty well with, but if you have any questions on those, of course, please come see me or send me an email, and I will see you guys in class later today.